We are almost to the point where I can teach you how to actually do hypothesis testing. But before we do that next week, I've got one more day where I need to sort of make sure that you're comfortable with what it is that we're doing with the normal distribution and how it is that our sample relates to the population. So today I'm going to teach you guys something called a confidence interval. And confidence intervals can be tricky, and I'll probably convince myself that I'm wrong at least twice today. And I'll have to stop and go back and make sure. Because confidence intervals involve us trying to make a prediction about the population from the sample that we have. And we're going to start using language that talks about probability, and there's a 95% chance of something happening. And you have to be very specific when you're talking about this. Right now, everybody is trying to guess what's going to happen next week in the midterm elections. And Nate Silver, who used to work for ESPN and the New York Times, I think he's with, I forget where he's with now. He had a blog called 538, and he was, he's in the prediction business. And in the 2016 election, Nate said that Donald Trump had a 16% chance of winning. Okay. He constructed a prediction model, and he said that Donald Trump had a 16% chance of winning. And what happened? Donald Trump won. So does that mean Nate was wrong? Cody? Is it other Cody? You want to say yes, right? Because he said that there was an 84% chance that Hillary Clinton was going to win. And she didn't. So you're like, Nate Silver sucks. And this is a narrative that the president has picked up on, right? All the polls and all the polls and predictors were wrong. But Nate, after the election, said, time out. I very clearly said that Donald Trump had a chance of winning, right? It was a low chance, but it was a chance of winning. It was 16%. He had a 16% chance of winning. A 16% chance is about the same if I hand you a die and I say, Johan's going to roll a 6. And guess what happens? Son of a bitch rolls a 6. That's about the exact same percentage. So Donald Trump rolled a 6. And Nate Silver was an idiot because he said Donald Trump has a 1 in 6 chance of winning the presidency. And everybody's like, oh, all these polls are garbage. Right? And Trump has this thing. The New York Times apologized. Bullshit. All right? They didn't apologize, not once. And they tried to explain why and how this happened. And it's because we don't have a good working education when it comes to probability. All right? So Nate Silver's back. It's the midterms. And guess what? He says that there's a 1 in 7 chance that the Democrats take the Senate, and there's a 6 in 7 chance that the Democrats take the House. So if we wake up next Wednesday morning and the Democrats have won the Senate, does that mean Nate Silver was wrong? No, it just happened that it hit on the 1 in 7 chance. And I find this really funny because I wonder how many millions of people bought Mega Millions and Powerball tickets last week when you had a 1 in 323 million chance of winning. Somebody in South, one person, one. Yep. And thanks to that, the state of South Carolina is going to see $64 million extra dollars in income taxes this year. Just off of that winner, assuming he's a state resident. Good for us. All right. So I think when we talk about probability and the chances of events happening, we need to like not focus so much on what the number is. He says as he's about to teach you something that has 95% confidence. But I do that to point out that that means that there's a 5% chance that what we're about to predict or we're about to try to compute might not happen. And that does not mean we're wrong, because we very clearly told you ahead of time that it was a 95% chance. Just like Nate Silver very clearly said it was a 1 in 6 chance. But you don't like the 1 in 6 odds when you're trying to select who's going to win the presidency. But you like 101 in 323 million odds when you pay money to play the lottery. And the best part is when you buy 10 tickets and you're like, I have a 10 times more likely chance. Yes, you now have a 10 in 323 million. Or a 1 in 32 million chance. But that's worth money. Okay. So we have to be a little bit careful. So what are we going to talk about today? Well, today we're going to actually get closer to real math. Because in order to teach you how these things work, we have to tell you that we know what the population data looks like. That we know what the population mean is, the mu, and we know what the population standard error is, or standard deviation is, the sigma. But we're going to be collecting data from samples, and we're not going to know what the population numbers are. So what we're going to do is we're going to learn about how to infer what the population numbers are given what we've observed in our sample. Kind of reverse engineering. So last week it was how likely are we to observe our sample mean given we know what the population mean is. Now we're going to reverse that and say, given we know what the population mean is, how likely is it that we can know what the see, this is one of those times I have to stop myself, go backwards. Last week, how likely is it that we observe a sample mean given we know what the population mean was? This week, how can we describe the population mean given the sample that we have? So we're trying to work backwards this time. So let's just start with an example. This is the way social science generally works. You start with a sample of observations. So let's say we're trying to understand salary data. Right? We're trying to understand what job we should go into based upon how much money it pays. If I had to do this all over again, I'd go into accounting, because a first-time professor of accounting at Coastal starts at $120,000, which is more than twice at what a starting salary is for a professor of politics. So same work, twice as much money. I have to learn about accounting, but there's worse things. That's what I'd do. I assume some of you, once you leave here, you would like to get a job and be paid money. Yeah? Okay. And then Allie's like, no, I don't need any money. I like living in the poverty of a student. All right. So here's an example. Let's say you want to know whether or not you should go into IO Psych, Industrial Organizational Psychology. So this organization, wanting to know more about its members, did a survey, and they got responses back from 36 members of their organization as to what their salary was. So we have a sample mean of professors' salaries. I don't even know if they're professors. They're just people who work in the field of IO Psych. All right. And we have sample statistics. We have a sample mean, X bar. We have a sample standard deviation, S. Now, given what we know about our sample, can we make an inference, a guess, an informed guess, a best guess about what the population of IO psychologists looks like? Again, we're going to work backwards. What we're going to generate is a population parameter. A population parameter. What is the population parameter that we're going to estimate? What are we trying to guess? I have a sample mean. What is it that I'm trying to estimate, that I'm trying to get an idea of what exists? Of the population. I want the population what? Yes, the population parameter of what? The I want mu, right? I want the mean. I want the population mean. That's the parameter I'm trying to estimate. Population mean, mu. I just want somebody to say mu. That's what we're trying to generate. We're trying to generate mu from our point estimate of x bar. The point estimate is actual data, okay? It's the 36 people we talked to. Now, if we draw different samples of different 36 people, we're unlikely to get the exact same answer, right? Y'all can appreciate that. Because when you draw 36 random people out of the thousands of IO psychs that are out there, you're going to get a different 36 people, and there's going to be variation in their income. You all agree on that, right? And if you're really smart, you should go, well, yeah, Dr. Wood, there's going to be quite a bit of variation because the standard deviation in our sample was $12,000. So that's a typical distance away from the mean, right? Isn't that the average distance from the mean? Yeah? So you should in your mind go, there's probably a pretty good range. And if some of you are thinking back to the empirical rule, you know that about 70% of them are a standard deviation away. So there's going to be a range between 68 and 44,000, which is a pretty big gap. Trust me, it is. Okay. So what we're going to learn about today is a confidence interval. We're going to come up with a range of values with a certain percentage confidence that we believe includes the population mean. Mu's in there. Now, when I say confidence, that's that percentage chance. So back to Nate Silver and his Donald Trump has a 16% chance of winning. What we're saying is there is a percentage chance, and we picked the number, that mu, the population mean, our parameter of interest, is in this range. Does that make sense? Okay. How do we do this? Well, the first thing that we have to decide is our desired level of confidence. How much confidence do we want? Typically, we choose 95%. Why 95%? Well, that mirrors the less than 5% chance that we typically use when we do hypothesis testing, right? Setting alpha at 0.05. This is following in that tradition. All right. If we were to express 95% as odds, this is a 1 in what chance of being wrong? Say it. 20. This is a 1 in 20 chance of being wrong. Okay. I'm willing, that's good numbers, right? A 1 in 20 chance. Yeah, 100 divided by the 5% that's missing, that's 1 in 20. Right? So 19 out of 20 times, we should be right. We're actually going to do the simulation. I'm not going to send you out there to find IO psychologists. But I'll show you a way that we can do the simulation. So that's the first step. And again, what level of confidence do we want? Now, because this is a book, a math book, that we're trying to teach you how to do this, all of the examples in the book are not 95%. Some of them are like, let's do 90%. Let's be really certain and do 99%. That's step one. Step two, calculate the confidence interval and the limits. Okay? So that's what we're going to learn how to do this. So we've had this discussion. How do we arrive at the desired level of confidence? How confident do we want to be? Well, we don't want to be 100% confident. The reason is 100% confidence basically says the average salary of an IO psych is anywhere between $0 and infinity dollars. And how helpful is that when you make a determination? Because that's the only way we can be certain, 100% certainty, to make sure that that population mean falls within our range of values. So you go to a POLI for a job, and you ask them. This is one of the things that you should ask on a job interview. What's the potential salary? Somewhere between 0 and infinity. Okay. Like you wouldn't know what to do with that type of person, right? Professor Wood, can I still get an A on this class? Well, your grade can be between 0 and infinity. That's not a helpful answer. Right? So the whole point of this is to arrive at something we have, I want to use the word faith in, but I don't want to use the word faith, that we have an understanding of likelihood about. But at the same time, we want it to be useful. So the 95% confidence intervals, we will be 95% confident that the interval of values we create will contain that unknown population mean mu. That's what we're going for. So this is how we do it. CI is our short for confidence interval. Looking at the math, confidence interval equals our sample mean, that's what x bar is, plus minus t times the standard error of the sample mean. This might be new to some of you. What does the mathematical symbol plus minus mean? Allie? Plus or minus? Which one? Yeah, it's not an or, it's an and. So how many times are we going to do this equation? Twice. One time we're going to do plus, and one time we're going to do minus. Why? Why do we have to do it twice? Because there's an upper boundary and a lower boundary. Allie, why is there an upper boundary and a lower boundary around a mean? Because it's an interval. And why do we just simply switch the signs? What is it about the distribution that we're using that allows us this plus minus thing? Come on, give me a word to describe the distribution. This is what, like week 5 that we discussed this? Might have even done it earlier. What about it? Normal distribution has this feature. That's why we're using t. Why is it plus minus? Because the distribution is symmetrical. Okay? So what we're doing here is saying the mean is the center. Okay? Our sample mean is the center. And we need to figure out how far to go out. And we're going to go in both directions. So to go to the upper bound, this way, we need to go in a positive direction. To get the lower bound, we need to go in a negative direction. I mentioned this last week. The standard error of the mean takes into account the sample size. What happens as our sample size increases to the standard error of the mean? So as n gets larger, what happens to our s here? It gets smaller. Why? It is a good question.
Because a higher sample size will give you more. It would leave less error to get the actual closer to the actual population standard deviation.
Why? You're right.
I know.
I didn't throw anything at you, but why? Why is it? There's two. You can give me two valid answers here. The first valid answer is, well, it's math. As your denominator gets bigger, the value of your fraction gets smaller. So when you divide something by 100, that's smaller than when you divide something by 4. Yes? Okay. It's the difference between a quarter and a penny. Okay? But let's think about this like not mathematically. Let's think about this intuitively. Why is it that when our sample size increases, the standard error would get smaller? The sample size means that we have what? More. Nope. Not more in the population. As n gets bigger, we have more what? More what in our sample? More scores in our sample. Okay. Why is that better? Because what? Okay, we have a potentially bigger view, all right? A bigger sample means a bigger view of the population. What are we getting closer to, though? Right? As our sample gets bigger, we get closer to what? The population. Okay? See, when I say population, I know instantly some of you are thinking the billions of people on the earth, because that's the most common way that we use that term population, right? So your brain is doing like a shortcut. Oh, the population, billions of people. How is it that you go from 36 to 76 that you get closer to billions of people? He's lying. Well, no, you can't infer that when I say population, I mean a ridiculously large number. You got to stop doing that. I know it's intuitive, which means you're not thinking about it when you're doing it, but the population is not always a ridiculously large number. Back to the example last week when I talk about how long it takes professors to get their PhDs. I can have the population of coastal professors pretty quickly. Right? It's not billions of people. It's a few hundred. A few hundred in a data set, that's nothing. That's a few hours. Right, Allie? Just a few hours of work in front of a computer for some research assistant somewhere. Right? It doesn't take that long. Right? So don't think that this population thing is always a massively huge, large number. It might not be. It could be a lot smaller than you think. How many countries are there in the world? Do we even know? If I said 200, would you laugh at me? Why are you going to laugh at me, Cody? Because you just want to laugh at me, jerk. Isn't it somewhere between 100 and 200 countries in the world? Come on. Anybody here take comparative politics recently? IR? No? Thank you. Google. How many countries are there in the world? I think it's like 200 and something, but that could be the number of bones we have in the body. 206? 195. Ha! Suck it. Look at that. 200. Got that one right. That's the population of countries. That's not a lot. Okay? So stop thinking about population and just say that there's a sort of larger number out there. So as our sample size goes up, our standard error gets smaller, which is good. All right. Now, how are we going to do this? Well, I've given you a chart, a t-distribution table. And unfortunately, I've given you one that doesn't have odd numbers on it for this example. Degrees of freedom. So what is the value of t? Why are we using t? Because it's a sample of a smaller size. And the trick is, once you reach a certain point, you approach the magical 1.96 number from a normal curve anyways. So just go ahead and just assume that it's okay to use t, right? It's sort of a redundancy. If you use t when you're supposed to use the z-score, there's no difference. But if you use a z-score when you're supposed to use a t-score, you get that question wrong. Okay? So that's why in the equation I actually write it as t, right? A t-score. So my chart doesn't have a degrees of freedom of 35. Let's talk about this degrees of freedom thing. Degrees of freedom comes from the philosophy of doing inferential statistics. And where it comes from is this idea that in order to generate some of these statistics, you have to have more than one observation. So if you have a data set of one observation, can you calculate a mean with a data set of one observation? Yes, you can. Whatever that value is, it is the mean, right? Can you calculate a standard deviation with only one observation? Because there is no deviation from the mean, because the mean is the one value. I use this example, even though it's not 100% correct, to explain to you that when you have one data set or one observation, you can really only generate one statistic, the mean. You can't generate two. You can't generate more statistics than the observations you have. So the way that this was explained to me was you have 36 observations. You're generating a statistic in doing this. You need to take out an observation to account for that statistic you're generating. So lots of times the degrees of freedom is n minus 1. Right? N minus 1 is the degrees of freedom. In like 3 statistics classes from now, if I'm teaching you multiple variable regression, and we have 8 statistics we're generating, because we have 8 different theories as to what influences our dependent variable, we have to have more than 8 observations. Right? But for you guys, for intro stats, we're usually only calculating one statistic at a time, one observation. Okay, is going to be taken away. That's why it's n minus 1. The more statistics you generate, the more observations you have to set aside to generate those statistics. All right, so degrees of freedom, n minus 1. That's where we use our t-table. And I know I went over this just in a video, and the first time I'm going over this with you live. If anybody needs a t-table, they're up here. You can come get one. But the way that the t-table works is our rows on the side are degrees of freedom. So degrees of freedom is 35. Again, I've handed you one that has even numbers on it. But the appropriate value is 2.042. So when you look in the table, okay. All right. Let's work our way through it. Here's our equation, our confidence interval. We have the sample mean. That was the 56,000 number. We're going to plus and minus our critical value of t that corresponds with the confidence interval that we want, 95%. We're going to multiply that by the standard error that we just computed. And we're going to go through the math. What's the thing that we do first? The first thing we do is the thing in the parentheses. We did that. We calculated it. The next thing we do, are there any exponents? No. Is there any multiplication? Yes. So the next step is to multiply these two numbers together. Let's see, that's PEM. Is there any division? No, not anymore. Is there any addition? Yes, the plus sign. So we do the plus sign first. 56,453 plus 4,127. It's going to give us an upper limit of 60,581. If we do minus, we get 52,000. Now you'll notice and you're thinking I'm an idiot for saying this, but you'll notice that the upper limit is more than the mean, and the lower limit is less than the mean. I had a student come in one time, back in the days where I was assigning homeworks, and they were having a hard time with this, and I was looking at what they were doing, and even though there's like 3 steps in this, somehow they were giving me a confidence interval that was completely on one side of the mean. Like it never crossed over. Like they put an extra negative, like they had, 2 or 3 extra negatives in there. And it's like, this, no, you can't do this. All right? I think they ended up with a negative standard error, and then it just was like, no, what are you doing? Right? So one quick and easy check to make sure that you've done this correctly is that you have a number that's both above and below your sample mean. You guys do some messed up stuff with your math sometimes. So what conclusion can we draw from this? Why do we say we're drawing a conclusion? Because we're not really rejecting a hypothesis. The reason that we say we're drawing a conclusion is because we need to explain what the event that we've calculated means. So there is a 95% probability, a 19 and 20 probability, or odd, that the interval of $52,325.76 to $60,581.40 contains the mean income for the population, mu, of recent master's degree recipients in IO psychology. Being chair of the department, I often meet with parents of prospective students, and one of the questions that parents want to know is how much money is my kid going to make when they graduate? And I very politely say, well, we don't really collect that data. But can you imagine, like, you guys have graduated, and so Sammy's going to graduate, and I'm going to just send her an email and be like, hey, tell me how much money you make. Where are you working? How much money you make? Like, there's no sense that, like, this might be information that people like to keep kind of private. Well, Dr. Wood, I'm making $16,000 a year. Great, thanks for the data point. I'm never telling anybody that our graduates make $16,000 a year. Yep, come get a degree and live in poverty. I'm not going to do that. But these parents, man, they're like, I want to know what job my kid's going to get. And I'm like, I don't know, Bojangles? Like, I can't help you out here. Like, not something I can do. All right. So finding salary data is one of those things that's a little bit difficult as a researcher to get. But it's something that lots of people want to know. All right. So that's the conclusion that we can draw. We have an idea of what the range in the population is. And that seems pretty good, actually, right? You graduate with a master's degree, and you're making somewhere in the $50,000 to $60,000 range. I'd say that was a worthy investment. You are now solidly middle class. Congratulations. Unless this is New York City, then welcome to poverty level. Enjoy your 40 square foot studio apartment. Don't live in Manhattan. All right. Here's what this looks like. Back to our friend, the normal distribution. We're inferring from the fact that we have this distribution of sample means that it's pretty much the same thing as the distribution of the population. So remember when I had my two curves on top of each other? Right? This is sort of saying that our distribution of sample means and our distribution of the population should be kind of the same. I ripped my thing, so I gotta do that anew. Right? So just sort of like you turn that, they should sort of be right on top of each other. So let's do that. Let's twist them, put them on top of each other. So what we're saying is that in the distribution of the population, I really like that he uses this word imply, okay, because we're working off of probability here. We're implying that 95% of our sample means should fall within plus or minus 1.96 times the standard error. The same exact procedure that we just used when we only had the sample statistics of the sample mean and the sample standard deviation. So if we were able to draw more than one sample, right? If we are able to draw repeated samples, every 20 times we do it, 19 of them should have a confidence interval that contains the sample mean. So we've got one, right? It comes close, but it's not guaranteed. That's what we're trying to do here. Right? So we have this one sample that we drew. We calculated the confidence interval around that sample. And we say there's a 95% probability that this confidence interval from point A to point B contains the population mean, mu. And we would have a 5% chance of being wrong. And we would be wrong for that sample. And that would mean all polls are garbage, right? No, it does not mean that. So I think this is the key takeaway. When we generate confidence intervals, it's the interval that we're talking about, the 95% confidence. It's not how close we are to the mean. Okay? It's the probability that the confidence interval contains the mean, not that the mean is in the interval. That's what we're actually doing. So it's not a 95% chance that the mean is in the interval. It's a 95% chance that that interval crosses that line, like on that previous slide, and has the mean. So it's a 95% chance that the bar crosses this spot here. That's what we're ending up with. Why do we do this? Well, because, like I said, there are lots of times when we do not have population information. Lots and lots of times. There are also times when we could have population information, but it would be really expensive to do it. So there's actually a story behind this tea distribution. And it's not the horse kick death story. This is the Guinness beer drinking story. It's a drinking story. Right? Let's say you're a manufacturer and you make a product. But testing that product to make sure that it works or is good requires you to consume that product. Do you want to test all of your product? No. Why not? Because then you would have no product to sell. Right? Think about this when you were a kid. Do any of you have fond memories of like cooking with your parents, like making cookies? Right? And the first tray of cookies comes out, and what's the thing that you want to do immediately when you're the kid? You want to eat the cookie. And so what do you say? I better test one, make sure it's okay. Yeah? Right? So I'm at your house, you're making cookies, you pull the tray out, and I say, I'm going to test them to make sure they're okay. And then I take a bite out of every single cookie on the tray. Is that going to work for you? I'm going to take a bite of every single cookie that comes out of the oven. No? That doesn't work for you, Sammy? Why not? I'll just one bite. I'm not going to say I'm going to eat the whole cookie. I'm just going to take just a nibble. Okay, you don't want to share. You don't even want to, let's say you have to bake them for your kids' class, right? And you're like, here, children, eat these once bitten cookies. The rest of it's fine. In fact, I can attest to you that that's a pretty good cookie because I had that one bite. I've tasted your cookie. It's a good one. And I only gave you the good one. You're like, no, right? You're not going to do this. Samsung got in trouble a few years ago. Does anyone remember about like 2 or 3 years ago the problem with Samsung phones? They caught on fire. Is that a feature of your phone? Like, I really love the flashlight thing, but I don't need the fire part of my phone. What happened? Guess what? Samsung did not test a sufficient number of their devices. Now, fortunately for a Samsung phone, when you test a Samsung phone, can you still use it after you've tested it? Yeah, right? So they can, put the ones on the charger and be like, let's see if it explodes. They didn't test enough of them. They were in a rush. They were trying to get their phones out. So they cut back on the quality control aspect of it. As famously seen in the entirely fictional film The Martian, where they're in a rush to get the supplies to the guy up in space in Mars, and they shoot the rocket up, and the rocket wobbles, and when it wobbles, it explodes. And it explodes because they didn't use real protein, they used soy protein, and apparently the soy liquefied. All because they hurried the testing process so the guy on Mars wouldn't starve. Again, a completely fictional film. We've never actually stranded anybody on Mars. Just the little robots we sent up. Okay. Students' tea, all of that to get to this story. Students' tea comes to us from the great folks at Guinness breweries. Why? Well, Guinness, before they send their product out, they do taste testing, like lots of products do. Right? Most food manufacturers do product testing. Guinness wanted to figure out how little product testing they could do and still have a certain amount of confidence in the quality of their product so that they could maximize how much Guinness they could get out the door. And there is only one way to test Guinness, and that is to drink it. Little side note here. Imagine your job is the quality control tester for Guinness. If you're an employer, do you want your employee to get shit-faced all the time? No, right? You want to keep them within acceptable levels of sober. So again, you also don't, trust me, it gets old after like 3 days, right? You don't want to have your taste tester consume that much. So you know what Guinness eventually did? They gave their employees bottles of Guinness on the way home. And they said, here, here's a 4-pack, go home tonight. And then if it was bad, they would come back the next day and said, oh, this bottle I had was awful. And then they could track down which cask was bad. I might have made that up. I don't know. Or the person who told me that might have made that up. It's been a while, okay? But this student's tea distribution comes from Guinness employing a mathematician to figure out how can we have a really small sample size and still get close to the sample mean. And if you watch that tea distribution video, you remember that the tea distribution is bell-shaped, but it has a little extra, room in the curves, in the tail part of the curve. They're up just a little higher. They're those little flyaways. Okay? So that's where the tea distribution comes from. It comes from a manufacturer, Guinness, trying to figure out how to reduce the product loss through quality testing. There is a way to do confidence intervals of the mean if you know what the distribution, the standard error, is in the population. It's about the same thing, but the equation is slightly different. I'm not going to go over this too much because, A, it very rarely happens. How is it that you can calculate the population standard error of the mean but not know what the mean is? Since in calculating this, the mean is one of the parts of the formula. So I'm not going to focus on that. But I will point this out because when you have a population parameter, you notice they switch over to Z. And Z for a 95% confidence interval is always 1.96 for 95%. The last thing I'm going to show you, I did this. Right? We talked about this, that as your n gets bigger, the size of your confidence interval should get smaller. The last thing I want to say about this is all of these equations you can reverse engineer. You can work them backwards. So let's say you know your confidence interval, you know the size of it, you know the features of your sample, but you just want to figure out how small or what size sample you need to have in order to get that level of confidence. So how many cookies must I consume to say that the batch of cookies is good? So you can work it backwards to try to generate the necessary sample size. There are some questions in the book that do this. I'm not going to put a question like this on the test, but I just want you to know that it does work both ways, that the equation can go backwards. So we know we have a 95% confidence interval. We can use our sample or some sort of estimate of the standard population standard deviation. And then we have our confidence interval. We can do that. It is possible. And you can go through and do that. Okay. Yeah, what time is it? I've got about 10 more minutes. The last thing I think we need to talk about No, I don't want to do it that way. I want to do it next week when we actually do hypothesis testing. I do want to mention this. One of the things that this highlights in calculating these in calculating these confidence intervals is that sample size has an effect on, not really the precision, but has a pretty good effect on our how we talk about probability. So if I go back to this slide, so this is that same example about the income of the recent master's graduates. You'll notice how the size of that confidence interval fairly dramatically shrinks as we go from 10 to 300. What do you think that would look like if my sample size was 60,000? You have no thoughts whatsoever. No thoughts? What do you think that band would look like? It would be smaller. What would it look like though? I can't even make it'd be like a wobbly dot. That would be your interval. Like the smallest you can get in between and still see space. Right? It would be really, really small. I say this because we actually have, and we're going to, in this class, use a data set that has a lot of observations. No, not the church. Here we go. So since we're right at the beginning of hypothesis testing and actually doing statistics, my advice to you for your course paper, where I ask you to do hypothesis testing, is to use this data set where the data has already been collected for you. It's a website out of UC Berkeley, the SDA website, Survey Documentation and Analysis. And the great thing for you is that in its archive, it has two data sets that are what we call an omnibus survey. It's a really big, long survey of lots of different questions that are about political and social things. One is called the General Social Survey, and the other one is called the American National Election Studies. The ANES focuses a lot on candidates for office, and so it tends to just ask questions. Actually, I should take that back. It tends to have a lot of questions about who people are going to vote for and about your political beliefs in public opinion. The General Social Survey includes questions about everything from spanking your child to pornography habits to illegally downloading things off the internet. I like the GSS because there's some really cool questions in there. And this is my suggestion for you for your course paper, where you're going to have to, your little 5-page paper, and prove to me that you understand how to do hypothesis testing using statistics. This is where I suggest you get your data from. And the way that this SDA website works, you have this user interface so that you can examine the data. But it also will allow you to create a custom data set that you can download and put into a statistical program, or in your cases, probably like Excel, to generate your descriptive statistics. Come on. The GSS has variable names that are actually a name of what it's asking. The National Election Studies just has like a string of numbers. So I like to use the GSS because I can say, oh, well, look at EDUC. EDUC is asking a person the highest grade in elementary or high school that you finished and got credit for. Which is somewhat confusing to me because it goes up to 20. Like, how can you do 20 years as the highest level of elementary or high school education? Like, if you're smart, you'll say 13 because that means you graduated high school. Well, how are people getting 20? Well, what they're doing is adding on the number of years afterwards. So you'll see a lot of people end up at 16. Well, A, they forgot they went to kindergarten, and they're doing 12 for the 12 grades, plus their 4 years in college. 16. But look at the total number of people who answered this question. 62,000 observations. Down here at the bottom where it says total. They have 62,000 observations. And you're going to be tempted to go, oh, I'm going to look at whether or not there is a difference between men and women going to college. Or, you know, my argument is that men are smarter than women because they have more education. So you're going to look at this variable. And you're going to have 62,000 observations. We have to be careful about this. And we have to be careful about it because, and this is the proper time to talk about this, remember when we're doing things like standard error, we're calculating the amount of variance that's in our data, and our denominator is whatever number over 62,000. What's that number going to look like when your denominator is 62,000? So if I take 4 and I divide it by 62,000, what's going to happen to that number? What's it look like? You got your calculator out? Oh, you mean you weren't actually doing the thing I was talking about? Okay, get off of Twitter and go on to there. There you go. Do 4 divided by 62,000. Wait, hold on. 0.0 4 zeros. It's going to be really small, right? It is going to be very easy to find statistical significance when your standard error is invisible because it's down to the millionth point, decimal point. 0, 0, okay, almost million. Okay? So we have to be careful about this. Why do we have all this data in here? Easy. Because because these surveys were asked in multiple years. And so what people are doing, if you don't, say, focus on a year, is, let's see if I can go to the end. They're adding together 1,600 observations from this year, 1,500 observations from this year, 1,500 observations from this year. So when you start playing with this data, because next week we're actually going to have a conversation about starting your paper, when you start playing with this data, you should ask yourself, should I be using every available year of the data set? Do I want to maybe show off and do my model that I'm doing by year to see if there are differences between men and women in the 70s, 80s, 90s, thousands, teens? Do it 5 times across the 5 decades of the sample. That would be shiny. Okay. The other thing about this is when people start looking at their variables and they come up with an idea. Let's see if I can find something about search. Have you seen an X-rated movie in either a movie theater? There was a time when people would go to the movie theater in public to watch pornography with other people. With other people watching pornography. That was a thing. Like the summer blockbuster. Just want to remind you all of that, okay? So that's the 1970s, public porn. Or on a VCR. Does anybody here actually still own a VCR other than me? Me and only like 3 of us, okay? Now the question would be like, how corrupted is your phone from Pornhub or other pornography website? Which actually are great for social scientists, because just like every other social media website, Pornhub collects a ton of user data and releases it. And so like researchers can go to get data from Pornhub about what people are doing, watching, searching. Yeah, okay. Well, look at this question. How many responses do I have? About, what, 503? If I had to guess, I would say that that question was only asked when? In 1 year. So if I get 2 interesting variables and I go to do my analysis, what you'll get back is you can't do it because the 2 interesting variables don't match up in the year that you use. So this is sort of a warning. So we're going to be careful about not running a data analysis on a data set of 62,000. And the cost of that, let's see, X movie 1. Is going to be that we can only use data from the survey from 1994. So if the other interesting question that you have, I have at least 3 people every semester that come in and they don't understand why it doesn't work. And I say, well, do you know what years you're using? And they're like, huh? Okay, so this one question was only used in 1994. Got 1 minute left. So one of the arguments of people against pornography is that it causes so many other social ills. You could, because this question was asked, if you want to make the argument that watching pornography leads to decentralizing or decentralizing violence or objectifying people, you could make an argument that as a result, people who watch pornography are more likely to commit crimes, spank their children, right? That question of spanking children was asked in 1994. You could do that. That one works. There's a question in here like, do you know anybody that's ever been murdered? I love that question because I can just imagine sitting down and be like, so, how old are you? What year were you born? Male or female? Da, da, da. Do you know anybody that's ever been murdered? That's not usually a first conversation question. Right? But as a person who knows somebody that's been murdered, I wonder how that would influence other events or other ideas. Would that influence my viewpoint on the death penalty, for example? It might. That would be an interesting research question. Does personal experience with violent crime change your attitudes towards criminal justice policy? So these are the types of things that as I'm teaching you hypothesis testing, I want you to start playing with this website, all right, and start looking at the data, because you, not me, you are going to have to write a 5-page paper where you show me that you've learned something in this class, and it should be interesting to you. So spend some time. The links in the course paper section are already up there. Everything there that you need to know is there. There's even already a video about how to play around with this data a little bit. Okay.